Unit 4 Review. The purpose of this video is to review the topics from Unit 4. Unit 4 focused on torsionally loaded members. I will review the topics stress, deflection, constrained deflection, and power transmission. Use the time shown to jump to a specific topic. Now I will turn the focus to torsionally loaded members. Torsionally loaded members are members subjected to moments about their longitudinal axes. Torsionally loaded members are sometimes called shafts. Like simple shear in a pin, torsional loads also cause shear stresses in shafts. However, the equation for shear stress is different. The stress is caused by an internal torque. That is what T represents in the shear equation. The Greek letter rho is the radial distance to the point where stress is being evaluated. We can see a representation of rho in the figure on the right. It is measured from the centroid of the cross-section to the point of interest at which we are evaluating stress. So rho is a distance between 0 and the outside radius of the shaft cross-section. The figure on the left demonstrates the significance of rho. The figure represents a theoretical cut in a shaft subjected to an internal torque. The small black arrows on the cut surface represent the distribution of shear stress over the surface. Note that the shear stresses are parallel to the cut surface. Also note that they change directions, depending on the location on the surface. They are acting in the direction of the internal torque. Last, note that the magnitude of the stress changes in the cross-section. At the center of the cross-section, when rho is equal to 0, the shear stress is 0. As we move away from the center, rho increases, and so does the magnitude of the shear stress. Note that the increase in magnitude is linear, as represented by the triangular distribution. The shear stress is maximum on the extreme outside edge of the cross-section. For this reason, we primarily take rho equal to the outside radius, since this is where shear stress is maximum, and therefore closest to failure. The J in the stress formula is the polar moment of inertia. Like area, polar moment of inertia is a cross-section property, and is only dependent on geometry, not material properties. Polar moment of inertia can be thought of as a resistance to torsion, and is calculated based on the cross-section radius. Note that as J increases, the shear stress decreases. For a solid cross-section, J is equal to pi over 2 times radius to the 4th power. For a hollow cross-section, J is calculated as the polar moment of inertia of the outside circle minus the polar moment of inertia of the inside circle. This is simplified in the equation shown. Don't pull the 4th power exponent outside of the parentheses. This violates the rules of exponents. The units on polar moment of inertia are typically in inches to the 4th power or meters to the 4th power. The deflection in a shaft is also called the angle of twist, and is given the Greek symbol lowercase phi. It is a twisting of the shaft about its longitudinal axis, and is essentially an angle of rotation between 2 points. Angle of twist is given a direction, positive or negative, based on the right-hand rule with the thumb pointing in the positive direction of the shaft axis. Like the axial deflection equation, the angle of twist equation has internal load, a torque, length, a material property, G, the shear modulus, and a cross-section property, J. An evaluation of units will yield that they completely cancel out in this equation. The units, therefore, are radians, an angle of twist. More general forms of the angle of twist formula are shown here. They are similar to those for axial deflection. In fact, we use the equations the same way we do for axial deflection. I will now review 2 scenarios where the general forms of the angle of twist equation are useful. In the member on the left, 2 concentrated torques are applied. Since the angle of twist equation is based on internal torque, it can be very helpful to plot an internal torque diagram. Here's the diagram for the member on the left. Note that torques acting counterclockwise are plotted as positive. based on the right-hand rule with the thumb in the direction of the positive x-axis. For the left section of the member, the internal torque is equal to T1. For the right section of the member, the internal torque is equal to T1 minus T2. Here it is negative since T2 is greater than T1. The jump to 0 at the right end of the graph is equal to the reaction torque at the support. If the cross-section and material property G are constant, then this form of the angle of twist equation can be used. The numerator of the equation can be written as the sum of the area under the internal torque diagram plot, being careful to take sign into account. In the member on the right, a uniformly distributed negative torque is applied along the full length of the member. A plot of the internal torque would look like this. The magnitude of the internal torque gradually increases as we move from left to right, and is at a maximum at the support, where all the external load is accumulated. Note that the slope of the internal torque diagram is the applied distributed torque. Here it's negative. If the polar moment of inertia and the shear modulus are constant, then this equation may be used. The numerator of the equation is equal to the area under the internal torque diagram. In this case, the area is a triangle. The sum of T times L is the area of the triangle, 1/2 times the base dimension, L1, times the height, little t times L1. Divide the sum of T times L by G and J to get deflection. The formula with the integral could also be used to get the same result. Capital T is a function of x, and here is equal to negative little t, the distributed torque, times x. Integrating would give us the same result as before. Here is a torsionally loaded member problem. We have a shaft from A to D. At point A is a concentrated torque, 50 foot-pounds, acting in the negative direction by the right-hand rule. From B to C, we have a uniformly distributed torque, 40 foot-pounds per feet, acting over 2 feet. And at D, we have a concentrated torque, 30 foot-pounds, acting in the negative direction. The diameter is given as 1.5 inches, and the shear modulus is 10,000 ksi. We want to find the maximum shear stress in the shaft. We also want to find the angle of twist at point A relative to point D. For both maximum shear stress and angle of twist, we need to know what the internal torques are. So I'm going to draw an internal torque diagram. I'm going to plot the internal torque in units of foot-pounds. I could convert it to inch-pounds if I wish, but I just want to demonstrate that I can save the conversion till the last steps. At point A, we have a concentrated torque of 50 foot-pounds being applied. So that's going to bump us down to negative 50 on the diagram. Negative because the torque is acting in the negative direction by the right-hand rule. From A to B, there's nothing happening, so our internal torque is going to stay constant. From B to C, we have a positive uniformly distributed torque being applied at 40 foot-pounds per foot. So because it's uniform, a uniform distribution, we're going to, and it's positive, we're going to see our internal torque start to increase gradually in a linear manner. And for every foot we move to the right, we're going to increase by 40 foot-pounds. So if we go over 2 feet, that's going to be a net total of 80 foot-pounds. So we're going to go from negative 50 up to a positive 30. Then from C to D, nothing happens. So we'll stay constant at a positive 30. Then at point D, we have a concentrated torque, 30 foot-pounds, in the negative direction. And that's going to bump us down to back to 0 at point D. And that means our shaft is statically determinate. This is a requirement to be able to solve these problems. Now I'm interested to know at what point we cross from negative to positive torque. I want to know the length from B to that point. At the start of point B, we're at a negative 50. And then the slope of this line is a positive 40 foot-pounds per feet. And it's going to move some distance x. And then at a distance x, it's going to be equal to 0. So I can solve this equation for x. And I get that it is 1.25 feet. And that means the distance from the point of 0 internal torque to point C is 2 feet minus 1.25, or 0.75. Now with my internal torque diagram plotted, I can find the max shear stress. It's going to occur between points A and B, because that's where our maximum internal torque is, and the diameter is constant. Here's the equation for shear stress in a shaft. And the internal torque we're going to take as 50 foot-pounds. For C, we'll use the radius. J is the polar moment of inertia. We're also going to need J when we compute angle of twist, so I'll just calculate it separately here. We have a solid shaft, so the formula for J is pi halves times the radius to the fourth power. I get about 0.5 inches to the fourth power. So I've input the values into my shear stress equation. Notice that I dropped the sign on 50. For shear stress, we just take the magnitude. The sign is somewhat meaningless. It's in foot-pounds, and I need to convert it into inch-pounds, so I will multiply by 12. And C is the radius, so half the diameter is 0.75 inches divided by J. And I calculate that the maximum shear stress is 905 psi. Now I can compute the angle of twist using this form of the angle of twist equation. I will use it first, and then I will demonstrate how to use the integral form. J and G are constant throughout the entire shaft. In the numerator, T times L, we're going to just sum up the T times L, and that's essentially taking the area under the internal torque diagram. And we can break up the diagram into two rectangles, A to B and C to D, and two triangles between points B and C. From A to B, the area is negative 50 foot-pounds times 1.5 feet. Next we have the triangle that starts at point B. It'll be the area under that triangle is 1/2. The height is negative 50. Make sure you get the sign in correctly. And the length is 1.25 feet. The next area is the triangle that goes up to C. Its height is positive 30, and its length is 0.75 multiplied by 1/2 because it's a triangle. And the last rectangle is from C to D, 30 foot-pounds tall, 2 feet long. And this is going to be divided by J and G. J is 0.4970 inches to the fourth power, and G is 10,000 KSI. That's kips. We're working in pounds, so I will put that as 10 million PSI. So let's work out the units here on the top in the numerator. The units on our torques are foot-pounds, and the units on our lengths are feet. So we've got pound-feet squared in the top. I'll leave pounds as pounds, but I need to convert feet to inches. So I'll multiply by 12 inches per feet, and I will square that. And now I have pound inches squared on the top, and I will have pound inches squared on the bottom. So all the units should cancel out. And I calculate that the angle of twist comes out negative 1.014 times 10 to the negative third. Units are radians. The negative sign means that point A on the shaft is actually going to rotate in the clockwise position. I want to resolve the angle of twist using the integral form. Now in this problem, J and G are constants, so they can be pulled outside of the integral, but internal torque is changing along the length of the shaft, so we will write torque as a function of x. And we'll need to split the shaft into 3 segments, from A to B, B to C, and C to D. In each of these segments, we can define the internal torque with a single equation. From A to B, we have a constant internal torque, negative 50. So our function, t of x, is just a constant, negative 50. And I'll integrate that over 1.5 feet. B to C is a little bit more complicated. It's a linear function. It's going to start at negative 50, and then there's a slope on that function. It's equal to the applied distributed load, which is 40 foot-pounds per feet. So we'll say plus 40x. And I'm going to say the origin is at point B, and we're going to integrate over 2 feet. So let's see, does this equation make sense? Well, let's see. When x is equal to 0, then this equation would give us negative 50, and that's what we have at point B, negative 50. When x is equal to 2 feet, then that'll be negative 50 plus 80, which yields a positive 30, and that's what we have at point C. So yes, we have correctly defined that function, and multiply it by dx. From C to D, we just have a constant internal torque, 30 foot-pounds. So that is my equation. So now I can evaluate my three integrals, and I get that the net area under the three curves is negative 35. If we recall from before, that's pound feet squared is the unit, so I need to multiply that by 12 inches per feet squared to convert into units of inch-pounds. And dividing by J and G, I get the same answer as I did previously, negative 0.014 times 10 to the negative third radians. So obviously both methods will work. They're just taking the area under the internal torque diagram and dividing by J and G. The next topic is constrained deflection of a torsionally loaded member. These types of members are also referred to as statically indeterminate members. An example is shown. The shaft has fixed supports at both ends. A free body diagram of the shaft looks like this. Summing torques about the y-axis yields this equation with two unknowns. There are no other useful static equilibrium equations, so this member is considered statically indeterminate. It cannot be solved with statics alone. We need another equation with the same two unknowns to solve for the reactions. We can use a deflection compatibility equation. Compatibility equations describe the deflection constraints within a member and are written in terms of deflection. Two methods for obtaining a compatibility equation are 1. The force method, and 2. Simply write a compatibility equation that constrains the deflections within the deflection limits available. Let's consider both of these methods for obtaining a compatibility equation. First, the force method. An example of a statically indeterminate shaft is shown. A single torque is applied at point B. Ends A and C are fixed. To apply the force method, we first remove a redundant or extra support. In this case, I have removed the fixed support at point A. Next, I find the deflection at the redundant support location from the applied loads. The deflection is shown as phi sub t acting at point A. Then I redraw the member. At the location of the redundant support, I place the support reaction that is actually occurring at the point in the original problem. I don't know its magnitude, so I will call it T sub A. I find the deflection at the redundant support location from the force caused by the redundant support. The deflection is shown in the image. It is phi sub A. Next, I write a compatibility equation that sets the deflection at the redundant support equal to 0. In this case, phi sub t from the applied torque minus phi sub A from the reaction torque is equal to 0. I substitute in the equation for phi. It is the sum of TL over JG. I can now solve for my unknown support reaction. The alternative method for finding a compatibility equation is to inspect the problem constraints and loads and determine a compatibility equation that constrains the deflections within the deflection limits available. In this case, we can imagine that when the torque is applied to point B will rotate in the direction of the torque. This means that point B will twist in the positive direction relative to C and in the negative direction relative to A. Since the supports cannot move, all deflections will have to take place within the bar. For the deflections to be compatible, the positive twist in section CB plus the negative twist in section BA must sum to 0. We can write that in a compatibility equation like this. Then we substitute in the angle of twist formula, written uniquely for each of the two deflections. With the compatibility equation and the static equilibrium equation, we can solve for the unknown support reactions. The example problem states, the shaft is composed of two segments of different materials. It is fixed at points A and C. A single torque is applied at B. Determine the support reaction torques. The torque is applied right in the center and has a magnitude of 5 kilonewton meters. We are given the shear modulus values G for the two segments. The shaft has a constant diameter of 50 millimeters. This problem can be solved with either the force method or the alternative method for determining a compatibility equation. I will use the force method. I apply the force method by breaking the original problem into two problems. By the principle of superposition, the sum of these two individual problems equals the original. With the force method, we remove a redundant support. There are two supports, one at A and one at C. I've decided to remove the support at C. With the support gone, point C is able to deflect. The deflection will be a rotation at point C from the applied torque. The rotation will be in the direction of the torque. I will call it phi sub t because it is caused by the applied torque. In the second part, I show the torque that is missing in the first. It is the reaction torque at point C. That reaction torque at point C is going to cause deflection at point C. It is going to be in the direction of the reaction torque. I know the direction of the reaction torque is going to be opposite of the applied torque of 5 kilonewton meters. I will call this angle of twist phi sub c. The purpose in breaking up the problem into two problems with the force method is so that I can write a compatibility equation. The compatibility equation is always written in terms of deflections. I know that in the original problem, the deflection at point C is 0. I will say that phi sub t is acting positive by the right-hand rule, with the x-axis pointing out from NC, and phi sub c is acting in the negative direction. Those two rotation angles must cancel each other out entirely. Or in other words, phi sub t is equal to phi sub c in magnitude. I can now expand my compatibility equation by inserting the angle of twist formula, which is the angle of twist phi is equal to the sum of TL over JG. First, I will look at phi sub t. In this case, I'm looking at this figure here. Phi sub t is caused by the applied torque of 5 kilonewton meters. If I trace the load back to the support, I can see that the load is acting over member AB, but member B to C feels no internal torque. This means all of this angle of twist, phi sub t, is occurring at point B, and point C just goes along for the ride. I only need one TL over JG term to describe phi sub t. For G, I will use the G for section AB, that is 50 gigapascals. Now I will look at phi sub c, that is the bottom picture. Phi sub c is caused by the torque, T sub c. If we trace back the torque through the shaft back to the support, we see that T sub c acts over the entire length of the shaft. That means I'm going to have two TL over JG terms to describe phi sub c, the term for A to B and the term from B to C. I have to split it into two because the value G changes. The torque T is T sub c in both terms. Each piece has a length of 1 meter. J is the same in both terms, but G is different. From A to B, the shear modulus G is 50. From B to C, the shear modulus is 30 gigapascals. Notice my mixed units. In the case of this compatibility equation, mixing the units is not a big deal because all of the units cancel out. Gigapascals cancel out. The 1 meter cancels out. J is the same in all three terms. It cancels out. So I will be able to solve for T sub c, and the units will be kilonewton meters. I simplify my equation, and then in the next step I will solve for T sub c. I find that T sub c is 1.875 kilonewton meters. I also want to find the reaction torque at point A, so I'm going to draw a free body diagram of the full shaft. I can now use statics to solve for the reaction torque at A. I find that the torque at A is equal to 3.125 kilonewton meters. Together, TA and TC both share the applied 5 kilonewton meter torque. Why does TA take more than TC? In this case, it has to do with the stiffness of the two sides. The stiffer member will always take more of the applied torque. And stiffness is affected by member length, member's polar moment of inertia, and the member's material property, specifically the shear modulus. In this problem, the length of each side and the polar moment of inertia of each side were the same. So it really just comes down to the difference in the shear modulus. AB is larger, or it has a larger shear modulus, and thus it is stiffer and takes more load. The example problem says, the shaft is composed of a tube with shear modulus 20 ksi, bonded to a solid rod of shear modulus 10 ksi. The shaft is fixed at one end and free at the other. A torque of 200 kip-inches is applied at the free end. Determine the portion of the applied torque resisted by the tube and the portion resisted by the rod. We're given the length of 36 inches. We're also given the cross-section. The tube has an outside diameter of 4 inches, whereas the diameter of the internal rod is 3 inches. 3 inches is also the inside diameter of the tube, and the two materials are bonded. This problem is statically indeterminate. We know that the reaction at the wall must be equal to the applied torque, 200 kip-inches. What we don't know is how much of that 200 kip-inches the tube takes versus how much the inside rod takes. Applying static equilibrium, we can sum the torques equal to 0. And we see that negative 200 kip-inches plus the torque in the tube plus the torque in the solid rod must be equal to 0. We have two unknowns. We need a compatibility equation. I'm going to use the alternative method for finding a compatibility equation, which is to look at the problem and, based on the deflection constraints, write a compatibility equation. When a torque is applied to the end of the shaft, the end is going to twist through some angle of rotation. Because the tube and the inside rod are bonded, they are both going to experience the same rotation, or the same angle of twist. So I can write my compatibility equation as the angle of twist of the tube is equal to the angle of twist of the solid rod. I'm going to substitute in the angle of twist formula, which is TL over JG for each of these terms. The length of both shafts, the tube and the rod, is the same, 36 inches. The applied torques will be different. We are given the shear modulus of each, and they are different, and also the polar moment of inertia of each is going to be different. So next I'll calculate the polar moment of inertia for the tube and the rod. The polar moment of inertia for the tube is equal to pi halves times the outside radius to the 4th power minus the inside radius to the 4th power. The polar moment of inertia of the solid rod is pi halves times the radius to the 4th power. Now I will expand my compatibility equation. The internal torque in the tube is the torque of the tube. We don't know that. The same is true for the rod. But we do know the lengths, we know J's, and we know G's for each. Notice that the length cancel out. The units, KSI, and inches to the 4th cancel out. I can simplify this equation as the torque in the tube is equal to 4.322 times the torque in the rod. I'm going to take my static equilibrium equation and substitute in 4.322 times the torque in the rod for the torque in the pipe. And now I can solve for the torque in the rod. I get that the torque in the rod is 37.6 kip-inches. And then solving for the torque in the pipe, I find it is 162.4 kip-inches. And the problem is done. Finally, power transmission in a shaft. The power transmission formula is power is equal to torque times angular velocity. Units can be tricky with this equation. In U.S. customary units, units for power should be in foot-pounds per second or inch-pounds per second. However, horsepower is often used. A helpful conversion is 1 horsepower is equal to 550 foot-pounds per second. Multiply by 12 to convert to inch-pounds per second. In SI units, Newton meters per second is used, and it is relatively trouble-free. Angular velocity should be in units of radians per second, but is often found in revolutions per minute, or RPMs. Convert revolutions per minute to radians per second by multiplying RPM by 2 times pi over 60. A common engineering problem is to design a shaft cross-section for a given power transmission, angular velocity, and allowable strength. This can be done by combining the power transmission formula and the torsion stress formula. Both formulas share the same T, internal torque. Knowing T and tau allowable, we can solve for shaft radius C. Here's a power transmission problem. It says, the power transmission of a solid shaft between a motor and a pump is designed to be 150 horsepower. The maximum angular velocity in the shaft is 400 RPM. Determine the minimum allowable diameter of the shaft to the nearest quarter inch if the allowable shear stress in the shaft is 30 kSi. We are given the conversion from horsepower to foot-pounds per second. Here is the power equation. I'm going to rewrite it to solve for the torque in the shaft. The power is 150 horsepower. We will multiply it by 550 to convert it to foot-pounds per second. Omega, the angular velocity, is 400 RPM, or revolutions per minute. We convert it to radians per second by multiplying by 2 pi over 60 seconds. Solving for torque, it is 1969.5 foot-pounds. Here is the stress equation for shear stress in a shaft. We're going to set it equal to the allowable shear stress. And since we were told that the shaft is solid, then its polar moment of inertia is pi halves times c, the radius to the fourth power. We have a c in the numerator and c to the fourth power in the denominator. So we can change it like this. Now I've solved the formula in terms of c. Now substituting in the variables, our torque is in foot-pounds, so we need to convert it to inch-pounds by multiplying by 12. Our allowable shear stress was 30 kSi. We need to convert it to psi. Solving for c, I get that it is 0.7945. Remember that c is the radius. We are asked to find the minimum allowable diameter. And multiplying our radius by 2, I find the diameter is 1.589 inches. Now this is the minimum required diameter. We cannot go below that. We were told to find the diameter to the nearest 0.25 or quarter inch. We can't round down to 1.5 inches because that would be too small. We'd exceed the allowable stress. So we will round up, and we'll use a shaft with a diameter of 1.75 inches. And we're done. This completes the review of Unit 4 topics.